let's talk about uh, IP fragmentation and assembly, reassembly in detail, because remember, we have a question mark on these three fields to discover it in details, that how a packet is fragmented and reassembled. So let's try to understand it. Okay, so in IP fragmentation and reassembly is allowed in IP version 4, right? And this is because these different links can have different maximum transmission unit size. For example, if this link is, let's say, an Ethernet link, this means I cannot have a frame size greater than 1500 bytes, because this is what this is. We know this. This is the maximum transmission unit size. So if I have an Ethernet frame, its size cannot be greater than 1500 bytes. Similarly, that means that it's a wireless link between these two routers. This means if it is Wi-Fi or wireless fidelity, the frame size cannot be greater than 312 bytes. Right, and similarly, over a long distance communication, maybe a link cannot have data size greater than 576 bytes, right? So now let's assume that this machine, it's a sender and it's the receiver. Let's assume that this machine has generated a TCP segment of size 4,000 bytes. So this machine has generated a TCP segment of size 4,000 bytes. And let's assume that this link is an Ethernet link. So this means at maximum, I can have a size of 1500 bytes. Right? So can I encapsulate this IP packet containing 4,000 or having a size of 4,000 bytes into a frame, or can I encapsulate into a frame having a maximum transmission unit of 1500 bytes? No, I cannot. So this means what? This means I need to divide this TCP, this IP datagram into 3 fragments, 3 smaller datagrams. So probably the first datagram can have a size of 1500 bytes. The remaining can also have a size of 1500 bytes, and whatever left is or will be placed in the third smaller datagram. And the reassembly is always done at the final destination. Why? Because at the final destination, the transport layer wants to have a one unified representation of TCP datagram, right, or UDP datagram. So that's why we have to do the reassembly at the receiver. So this means the fragmentation and reassembly, where it's important, where it's required, we have to divide the IP datagram into smaller segments, and for that we need to have these 3 fields: 16-bit identifier. We have these flags, the don't fragment flag, more fragments flag, and then the fragment offset. Right, and let's try to understand this with the help of an example. Let's assume that the length of an IP datagram generated by the source, as was the case in the last slide. So this IP datagram has a size of or length of 4,000 bytes, and I have a link of Ethernet where the maximum transmission unit size is 1500 bytes. So what I have to do? Yes, I have to divide this larger IP datagram into 3 smaller fragments. And in order to do this IP fragmentation and reassembly, I'll be using these 3 fields, right? Identification, fragment flags, and fragment offset. Right. So the first fragment can be of length 1500, the maximum length that is allowed by the MTU of Ethernet, which is 1500 bytes. And every IP datagram has an identifier, uniquely identified. So I'll take the identifier and I'll copy all this identifier of larger IP datagram into all the smaller fragments. Why? Because this will indicate that all these three smaller fragments are part of a big IP or a larger IP datagram, right? So you can see that I have copied the same identification field in all of these three smaller datagrams. And now the situation of flags is, so we have a don't fragment flag, we have more fragment flag here. So don't fragment flag is 1. This means that we do not allow further fragmentation of this smaller datagram. And then more fragment flag is 1 means what? This is not the last fragment of this larger IP datagram, because more I'll be sending more fragments as well. And then we have this offset field. And offset field is calculated by dividing the first data byte number by 8, right? Since since the fragments must be the fragment size must be the multiple of 8 bytes, except the last one, obviously, right? So let's assume the starting byte number is the data byte number is 0. So I'll divide 0 by 8. Obviously, it's undefined. I'll have the first offset value, which is 0 here. Okay, so I'll discuss in a minute what's the utility of this offset. Okay, so then I'll send the next smaller segment. The length of the next smaller segment can also be of equal to maximum transmission unit size, which is 1500 bytes. It has the same ID, and the situation of the flags are that don't fragment is 1 and more fragment is also 1. Why? Because, yes, because this is not the last smaller fragment of sequence. And then I have to calculate the fragment offset by dividing the starting data byte number. So here I transmitted how many number of data bytes? It was the total length, by the way, 1500. So 1500 minus the header size, which is 20 bytes. So this means the size of the data is 1480. Right? This means it goes from 0 to 1479. So what will be the starting byte number of this smaller datagram? Yes, the starting byte number will be 1480. So I'll divide 1480 by 8 again, and the answer is 185. And then I have this fragment offset of 185, right? And then whatever is left will be encapsulated or will be sent in the last smaller segment. And here the identification field is the same as was the case in the other smaller datagrams, and the field of the don't fragment or more fragment flags is as given here. So don't fragment flag is set, and more fragments flag is 0. This means this indicates the more fragment flag 0 here indicates that this is the last smaller datagram of this larger IP datagram, right? And here the fragment offset is 370. And how it is calculated? So what was the total length that I have transmitted in these two smaller segments? 1500 plus 1500 means 3000, and allow me to minus the header length of these two smaller datagrams, 20 bytes of this smaller datagram and 20 bytes of this smaller datagrams, 40. So this means 2960. And if I start from 0, so the data that I have transmitted so far is from 0 to 2959. So then what will be the starting data byte number here in the last fragment? Yes, 2960. So I'll divide 2960 with 8, and the offset is 370, right? So in this way, what we have done is we have divided a larger datagram into 3 smaller datagrams, and these 3 smaller datagrams can take different paths to reach the destination. By the way, what is the length of this last datagram? Yes, how? What was the total size that I was supposed to send? Yes, 3980. Why? Because this original larger IP datagram a size of 4,000 bytes. So if I minus the header size of 20 bytes, so the total data length would be 3980 bytes. So 3980 bytes minus what? 1480 transmitted in the first minus 1480 transmitted in the second segment. So what this will give me, whatever this will give me, this should give me 1020, right? So this means this is the data length in the last smaller fragment, right? Or datagram. And I'll add 20 bytes of header, obviously, of this last datagram. So the total length would be 1040 here. Right. So now let's assume. There's these 3 smaller datagrams take different path to reach the destination and can arrive, as discussed earlier, can arrive out of order. And let's assume that packet smaller datagram number 2 has arrived first. So I need to identify where to place the data that is being carried by or encapsulated by the smaller datagram 2. So what I'll do is I'll multiply the fragment offset by 8. So this means I'll get, so what I'll do is I'll multiply 185 by 8. So I'll get what? Yes, you're right, 1480. So I'll take the data, and the starting byte is 1480, and it will go up to, yes, 2959. And now let's assume that after smaller datagram number 2, datagram number 1 has arrived. So I'll again take the offset and will multiply it by 8. And what is the answer? Yes, 0. So this means I'll place the data inside the IP smaller IP datagram here from 0 to 1479. And then let's assume that at the last we have this fragment number 3. So I'll again take the fragment offset, we'll multiply it with 8, and this will give me 1. Yes, you're right, 2960, right? So the fragment offset helps me to organize or place the data encapsulated by the smaller segment in their appropriate places, right? But there are some problems and complications with this IP fragmentation and reassembly, which is important to be discussed here.